let us recapitulate what we have learnt in the last lecture. We have basically looked at the meaning of the thermodynamics, and later on we looked at the historical perspective of the thermodynamic, how the thermodynamic was evolved as a mature subject, and its application. We have looked at some of them which are quite magnanimous. It encompasses all the branches of science and engineering. So, therefore, it is a very important subject which I urge upon you people to take it seriously and study it and apply it to your professional and personal life. And today we will be discussing about various aspects of the thermodynamic, basically the initial concepts. And before starting this lecture, let us look at this statement by Max Planck, who says that we have no right to assume that any physical laws exist, or if they have existed up to now, that they will continue to exist in a similar manner. That means, he is challenging to you people to challenge the existing laws and find out what its are, what you call limitations, so that you can find out better laws of the nature or the physical world. So, when we talk about this thermodynamics, we are basically looking at the energy and in interaction with the matter. That means, we will be looking at the matter, and we use basically two approaches. One is macroscopic approaches, other is microscopic approaches. And what is the meaning of this macroscopic approach? In the thermodynamic, we will be using both approaches, right? One is macroscopic approach and other is microscopic. For example, like if I take a cylinder here, right? If you look at this cylinder we are taking, and it will be containing certain amount of gas, right. If you look at this gas and if this cylinder, can anybody look at this cylinder and tell whether it is contains oxygen, whether it contains air, or whether it is contains some other gas? Can anybody tell me? Actually, as an engineer, you should know the color code, right? If you look at this, the lower portion is which one? Black color. The upper portion is white color. Can you see? Right? And from the color, and if you know the code, then you can say what it contains, right? Of course, that one has to look at. I will urge upon you people to look at the color code of the gases. As an engineer, you must know. Whatever the engineer you may be, if you are in a shop floor on the plant, you need to know that. So, this basically contains the air. Of course, the color code will be different for different countries, but nowadays it is what you call homogenizing, and we do follow international standard, and this basically is a black and white color. If it is, then it is basically air. So, when you look at this kind of a circular cylinder which contains certain amount of air, and air means it will be mostly the oxygen and nitrogen. Of course, there will be several other gases will be there which you are very less percentage, then we are not bothered about it. And these are the two gases which will be at higher pressure, because it is a pressure cylinder, right. And when you talk about it, what is happening to the molecule? Let us say two molecules are there, oxygen and nitrogen. For the simplicity, we are assuming air consists of oxygen and nitrogen, and they will be moving around, right. They will be colliding, they will be interacting with them. And then if we look at those things, we call it as a basically microscopic microscopic approach, because each molecule has to be tracked out. But in engineering sense, we will not be looking at that, we will be looking at grossly. That means, if the what is happening to the pressure. For example, if you look at this cylinder is having some gauge is there, this gauge are there, and this is known as pressure regulating valve. Now, what are the kinds of valve? Pressure regulating valve will be there, right? How we can regulate the pressure is a question. From the cylinder, one has to regulate the pressure, otherwise you will be in deep trouble, am I right? If without this, without pressure regulator, if I use, what will happen? There will be some accident. If we handle the high pressure gas cylinder without a pressure regulator, accident will occur, right? So, one has to be careful. And if you look at the gauge, this gauge is basically pressure gauge, and by that we can measure the pressure. And the pressure, if you look at, is manifested due to the what? Change of momentum by the molecules on a particular surface, right? And we can also measure temperature and pressure, we can also measure the volume, and these are basically properties of the space average property. That means is average, right? We are not bothered about individual molecule interaction with that. And these properties, when you look at in a macroscopic way or in a what you call gross way, we call it as a microscopic property. And it basically talk about the average properties, it is not changing with respect to time. Of course, one can measure the pressure and temperature with respect to time, but in this example we are saying what it would be, right? And this is the average species. Now, why you will be looking at macroscopic properties? In our this course we will be mostly dealing with the microscopic approach to analyze the problems, because that will be easier, and no need to consider the structure of motion. There will be molecules, what is the structure, whether it's bimolecular, dimolecular or trimolecular, whether it is interacting, right? What is the extent of molecular activity? We are not bothered. We are bothered the gross effect, what is the effect, right? For example, if I look at your face and you are looking good, or you are very satisfied or you are attentive, but in your mind there might be several things which are going on, which I am not aware, right? So, when I am looking at gross, then it is basically gross properties I am trying to observe on your face or on your activities, right? But in your mind what is happening, that is the basically microscopic approach. So, now if you look at few variables are required to describe the system, if you look at the system or whatever it is. So, you can very few properties you can use it, and variables are easily measurable. These are you can measure pressure, temperature, volume, these are the things or other properties you can measure. So, therefore, we will be dealing with this macroscopic approach to analyze the thermodynamic problems, and this thermodynamics is known as classical thermodynamics. So, in this course we will be basically dealing with classical thermodynamics, where we will be looking at macroscopic properties, or the macroscopic approach will be utilized to analyze the problem. Just to give you a glimpses of what is the meaning of microscopic approach, let me just that we can take this same cylinder contains large number of molecules, as I told, like it can be in case of air it is oxygen, nitrogen, but it can be several other molecules, kinds of molecules, and which will be random motion, right? It will be all the time moving, and it will be have their own velocities, because it will be colliding, and then velocities may be changing of the each individual molecule. Not all molecule will be having same velocities, right? It will be changing, and as a result what will happen, like we need to look at, for example, if I take a small slice from the cylinder 1 centimeter cube. So, if you look at how much particle it will be there, it will be having something 10 power to 20 particles, means molecules you can say, right? Particles means you can think of molecules, and these are very big numbers, right. Now, I want to look at each individual particle, how they are doing. So, what will happen? The state of particle can be specified by the coordinate system. If you look at the coordinate system, right, if I take this as, if it is, this is your what you call x, and it is having I can say, right, and this is your y, and perpendicular to this, is your z. So, now the coordinate system has to be, and each molecule, this is fixed, and then your each molecule will be moving around, right. If it is having a molecule, let us say here, right, it is having a velocities in the x direction, right, v x, or it can be v y, and it can be v z direction, right. And when it is having, then you will have to look at the also momentum, how it is, right. The momentum can be mbi, mbj and mbk, right, unit vectors ijk, and it can be change in the momentum you will be talking about and other things. So, if you look at number of variables will be enormous, and if you want to solve this equation of motion and then finding out interaction, all those things, it will be enormous. Even the best computer cannot solve this and finding out its effect, right. Now, how to deal with it? Even if I will take a 1 centimeter cube as this thing and look at, and if it is a cylinder, if it is a let us say sun, if I look at the sun, lot of molecules will be there, like lot of nuclear what you call fusion reaction will be going on, and then other things, how will I analyze? Are you getting? So, therefore, even small systems, it is very difficult to look at, take care of each one, track of all those things, and then look at what will be its effect. For example, India is a populous country, 130 crore people. If I look at each individual, what is doing, how it is doing, what are the moving, how it is interacting with each other, one will go mad. Similarly, when you talk about these molecules are moving with a certain velocities, interacting with each others, and then keep track of them and what is happening, what are the changes occurring, it is quite difficult and enormous. Even the best computer cannot really compute within the enormous computational power. Now, how to deal with that? Is there any other way of looking at in a molecular level interactions and extent of molecular activities? Is it possible? There comes to the picture here what you call the tool, what we call statistical tool, right. So, it being used, and such an approach where you will be able to look at the microscopic effects, like each individual particle or the molecules, even sometimes if it is other things like atoms, then you will be basically known as the microscopic approach. As I told, that state of gas which changes continuously, because all the time, with the time it will be changing, each molecule will be interacting with other molecules, and then we use tools known as statistical tools to deduce these average properties, which we will be more interested in, right. So, therefore, statistics comes into picture, and this thermodynamic is known as the statistical thermodynamic, and microscopic means it will be dealing with with the matter at a molecular level. So, in this case, large number of variables to specify state of the matter, and the variables cannot be measured easily. If you look at, if I want to look at a molecule and it is interacting, what is its mass and what is the velocity is very difficult to measure, it is not really, and it is impossible to tackle even a simple system. And therefore, we use the statistical tool and the thermodynamic related to that thermodynamic that uses the statistical tool, which is known as the statistical thermodynamic, which is the beyond the scope of present course. We will be not dealing with. Maybe you people are interested in that, you can take in other courses in our institute, maybe in the Department of Physics and Chemical Engineering they do offer. So, how However, sometimes I will be looking at little give you a flavor of the microscopic approach whenever we are discussing about that, not maybe in on some occasion. Now, whenever we are looking at these physical properties, right, we need to look at the its dimension, because the physical quantities, right, will be characterized by the dimensions. What do you mean by these dimensions? Any idea? Any idea what do you mean by dimensions? Because if there is a physical quantity, then we will have to assign something like to the mind. For example, you say the length. For the length we will have to say it is a meter, right, or a time for the second, like that. And if you look at this physical quantity can be into two categories. One is primary quantities like a length, mass, time, temperatures, and similarly like you can have a certain derived quantities like your velocity, acceleration, right. Like velocity is basically change in displacement with respect to time, and then A is your acceleration, change in velocity with respect to time, and force, and then pressure, force per unit area, and other things like energy and other things. So, whenever this arbitrary magnitude being assigned to this dimension, we get the units. So, for example, earlier days people are using this British system, that is the feet, right, pound and second degree Fahrenheit, which are quite clumsy, because it is not really very good. For example, if you look at the foot, it will be something 1 feet is equal to 30 inches, and inches again will be little difficult to soothe and other things. There is several earlier days in our country also we are using British system, but later on we found that which is quite congruent with the decimal system, that is the SI system or MK system. So, that is being used metric system. In the metric system, that is called like MK system, that is meter, kg and second, right. In CGS system we call centimeter, gram and second kind of things, and this is being used very much. Of course, if you go to our market or something, people are still using the British system, although it is to use. And international level we use the SI system, basically it is the international systems, and we will be using in this course SI system, but sometimes some problem may be given in other units, so that you know the unit conversion kind of things. So, in SI system we call it basically meter, kg, second and Kelvin kind of things. So, if you look at the international standard being used for mass, length and time and temperature. So, these are the standard which are being used. For example, like basic SI units for mass is kilogram, and a standard alloy block of platinum iridium maintained at IBWM. This is the International Bureau of Weight and Measure, and Severius in Paris. It is being kept because platinum iridium kept so that it won't change with respect to time. It is a very metal like which won't be corroded and eroded. Similarly, earlier days people were keeping the metal length and then they are saying this is 1 meter, but nowadays it has been changed. People are saying length of basic SI unit is a meter, which is equal to the length of something 16 lakh 50,076.73 wavelength of krypton 86 radiation, corresponding to transition between 2p10 and 5d in vacuum. So, this is a more precisely one can think of, because this is the standard which is being utilized for making it being utilized. Otherwise, if the standard primary calibration, or you just calibrate all the thing with that, that should be as accurate as possible. Some of you who will be conducting experiment or other thing, and the calibration is very important, because which is the baseline. The baseline is very important, and that should be as accurate as possible. So, similarly, if you look at SI unit for the time denoted as second in duration of this big number like 9, 1, 9, 2, 6, 3, 1, 7, 7, 0, periods of radiation of 2 hyperfine levels of downstate of cesium 133 atom. I am not expecting you will remember, but you should aware that what is the preciseness of this, because this is the baseline, right. So, and temperature, of course, in recent time people are using the triple point of water in that is in Kelvin, is basically expressed in Kelvin and taken as 1 over 273.16 of the triple point of water, right. Earlier days, we will be discussing as we go along that people were using basically the steam point and ice point as the reference, but now the triple point is being accepted worldwide because of its preciseness. So, if you look at, we will be using various quantities, System International like of course 96 they have adopted, and we will be using the acceleration is, as I told, the acceleration is basically change in the velocity with respect to time, this meter per second square, and the force is the basically F is equal to m a kg per meter second square Newton. See, Newton is the name, therefore, we will be using is as a capital N, not a small n, right. Any name, whatever we use always capital, right. That is the unit symbol we will be using. And the pressure, if you look at the pressure by definition force per unit area, and the unit of stress also is same as that of the pressure, because this is the normal stress one can think of, and it is ascribed with the Pascal, therefore, we call Pa, P is the capital A is small, and work or the energy is basically assigned with the unit kg meter square per second, because the force, right, and length, this is a meter square by second square, right. And it is you can think of using basically the Newton and meter, because kg meter second square is nothing but your Newton, right, and second that is a meter, and that is basically joule is being used, and this is J, and power is the rate of change of work, and which is nothing but what you call the work per unit time, and this we call it as a Newton meter, that is the work per second is a watt. So, you will be using this symbol basically as a capital. Be careful, because people do fuss about it if you are not writing it properly. So, I will just give you small tips like how to use this thing in your convention for using the units. Whenever the any unit, right, is after the scientist name, for example, joules, watt, pascals, newtons, and other things, coulomb, right, this will be with capital letter, okay. And for example, 10 Newton, 1000 pascals, right, it will be P will be capital Pascal and A will be small, and all others are in small letters. For example, 10 kg and 20 meter per second, right, okay. And if I will say it is kilometer, what it will be? It will be also small letter. But if you go to your highway, sometimes people write in capital, am I right? Did you observe that thing? Whenever you are moving in the looking at the signboard, you will find in some places it is written in capital letter, am I right? Particularly you can see the Lucknow and the Kanpur highway, right. You did not observe, you could have observed, just observe that, it is not right. So, and we will have to be little careful about when you say Newton meter, there should be a gap right here, and if it is millinewtons, we will have to say m and n, there is no gap. So, you will have to distinguish between this thing. And For example, you want to write 10 Newton or 100 Newton, do not write Newtons, you write 100 Newton or 10 Newton. The plural one should not use, and one prefix should be used. For example, milligram, right? mg is basically milligram, right? Or kilojoule, k should be small and j should be capital. But a lot of people I have seen they write either k is capital, j is capital, or k is small, j is small. Am I right? I have seen. And let us say MW, what is the unit? MW? Megawatt, right? But I can write down kilojoule, k, j? Can I write? I cannot. Okay? So, only one prefix should be used. So, no space between prefix and units. For example, if I say 5 into 10 power to minus 3 Newton is equal to 5 millinewton, you should not write 5 m, there is a blank and then Newton, one should not write that way. So, one has to be careful and also develop and have it so that you will not make mistake in writing, right, and no full stop should be placed at its end, right. And you might have seen people are writing 120 k dot and m dot, that means 120 kilometer on the signboard, which is not right, and they will be writing in capital also, that is also not right. So, one has to be careful about assigning the units to this thing. So, let us take an example which I have taken a very simple example. A tank of 2 meter cube volume is filled with kerosene of density 850 kg per meter cube. Determine the amount of mass m in the tank. So, we will have to do that. What you will have to do is very simple, right? You are given density, you are given the volume. So, basically the density is equal to m by v, and you will find out mass is equal to rho into v, and you just plug in the numbers and you will get. And if you look at unit wise, that left hand side here mass is kg and density is kg per meter cube and volume meter cube. So, cancel it out is kg, right. And if you put these values, you will get this number. This is very simple one. What it indicates? You might be thinking, why I am showing this simple example? What is indicating? What it is? This example, what you have learned is a very simple, like you use a formula and plug in number, you will get. It says that left hand side unit is same as the right hand side unit, what we call dimensional homogeneity. That means a mathematical equation should be dimensionally homogeneous. Am I right? That is the first thing one has to check whether it is right or wrong. And that means if it is dimensionally homogeneous, is it right? The equation need not to be right, okay? But that is the first condition, is a mathematical formula must be dimensionally homogeneous, but dimensionally homogeneous mathematical relationship should always not necessarily right, okay. It may be right, it may not be right. So, therefore, one has to be very careful. Interestingly, I must share with you, in the last semester I gave an example to the student in the examination, okay. And that subject was not covered, but I just gave so that he can use the dimensional homogeneity and answer the question. I will tell you that only maybe 10% people could answer that question and 95% couldn't answer, and it was a very simple, as simple as this question, right. So, therefore, I would suggest that be careful, in the sense it is a tricky question, not tricky, it is just to recognize whether you know this or not. And you may say, look, it is out of my course. It is not, right? It is a simple thing what you will have to require little presence of mind, and which people didn't do, that I had experimented. So therefore, you need not to think that why is, like giving a simple example. But this is not only a simple example, it is a very profound example for illustrating the dimensional homogeneity of the equation, mathematical equation. Now we will be looking at the definition and concepts of the thermodynamics, which is very important. Why we need to look at definition and concepts? Because like every subject is having their own vocabulary. You need to understand the words or the vocabularies of a particular subject properly and precisely, so that misunderstanding in that subject can be avoided. Therefore, one has to look at the definition and concepts, and most of the things you will be aware in your +2 labels science. But however, we will be again redoing it, so that it will be seep into your mind, and so that you won't commit any mistake in doing that. So therefore, you please listen it carefully and also try to think about it, what it is. So when we talk about a thermodynamic, we call it as a system. So what do you mean by a system? Can anybody tell me? See, as in the thermodynamic, which will be looking at energy and its interaction, right? It means interaction with a with its surrounding, one can think of, right? Now we need to define, and also we will have to take whenever there is a energy exchange taking place, there will be some change in the properties, and that means it will be properties will be changed only through the what? Only through the matter. Then only you can think of. We have already seen microscopic and macroscopic. Without matter, can you think of? You cannot think of a change in the state of a any interaction is taking place. So therefore, we can define a system as a quantity of matter or a region in space bounded by the closed surface. For example, if I take this room, I want to find out how much energy we are utilizing, right? And we will have to look at how many light points are there, whether it is coming, let us say sun is falling on this room and some energy is entering into here, and maybe there is a AC which will be on, and how much cooling air it is giving. So I need to find out. For that, what I will have to look at? I will have to make this in this room, and then as a system, and then we will have to say that it will be reacting with the or interacting with the surrounding. So if you look at everything external to the system is known as surrounding, and system and surrounding together we call it as a what? Universe. So if I look at a system here, right, and it is having a boundary, and rest of the things will be surrounding, and this total we call it as a universe. Let me take another example. I am having a cup of coffee here, right, and now this temperature is higher. Cup of coffee, when I say the temperature will be, let us say, higher, hot coffee, and it will be interacting with the surrounding. So what will be the is surrounding? What it will be? For example, if I take this, let us consider this is the cup, and it contains some amount of hot tea, let us say, right, and now it will be interacting with the what you call with its surrounding. What will be surrounding? Suppose the temperature is there, let us say I will keep this cup here on this. What will be its surrounding? The system I can take the whatever the hot tea is there, let us say I am saying this, I can take this as a system right, or I can take the full cup as my system, right. I am having liberty to choose that. Now I am interested to find out, like it will be interacting with surrounding, that means some heat will be transferred, right, some heat will be transferred to its surrounding. What will be its surrounding? Suppose I am keep placing a, what you call a cup, tea cup here. Can I say that a surrounding will be there where you are sitting, let us say maybe 10 meter from this, or can I talk about 1 meter? Can I talk about 1 meter is possible? 1 meter from the cup? It cannot be. Some of you are saying yes, no. Why? Because you cannot have any change. If I put a thermometer 1 meter from the hot tea, can it sense any temperature? It cannot. Am I right or wrong? So it will be closer to that where there is a change, there is a heat transfer is taking place, and if heat transfer is taking place, the temperature, let us say this is something maybe 50 degrees Celsius and this is something 25 degrees Celsius, right. If the change is occurring and then because of heat transfer nearby places, then only we will take its surrounding. So if you look at my surrounding will be very closer to my hot cup, where the physical properties are changing due to the interaction of this system, what we call it as a hot tea, with its surrounding. Is that clear to you people? So generally people say, look, this is my system and this is my surrounding. No, wherever interaction taking place, then only we call it as a system. So as I told that boundary, is a very important, because that separates the system and surrounding. Now how to choose the boundary is very important. It can be real, it can be imaginary, right, in nature, but how to choose which is the right boundary is very important point one has to look at, because that boundary will be defining the system. So as I told, it can be fixed boundary, it can be rigid boundary, movable boundary, right, and it can be diathermal, that means heat transfer can take place between the system and surrounding through the boundary, right. For example, I took that example of hot coffee, through the wall of the through the wall of this tea cup, then heat has to transfer, right. And this boundary, can I take that whatever the thickness of the tea cup, can I take it as a boundary? Mathematically it is not right. Mathematically we take is a thin boundary, right. And if this heat will transfer through the boundary, then we call it diathermal, and there will be some boundary which won't allow the heat to transfer, we call it as a adiabatic, right. Most of the cases, like air conditioned room like this, where the wall should act as an adiabatic wall, so that heat will be not transferred through that, otherwise you will have to pay penalty, that because a lot of heat will be entering into the room and then the cooling load on your air conditioner will be higher. So therefore one has to insulate it properly. And if you look at, just to summarize, the boundary can be fixed, it can be rigid, right, it can be movable. For example, I have already given you this example, like system, I can take this as a thing, as a wall of this room. If I take this room, I can take this room as that. That means wherever you are having interaction, right, that you will take as a system and boundary. And in the movable systems, for example, there is a piston cylinder which you use very often, like can you tell me where you use your piston cylinder? Right, wherever you use, you will be using in your day to day life, am I right? Yes or no? Right? For example, nowadays water crisis across the country, you do know, you are aware, we use the hand pump. In the hand pump, right, it will be a piston and cylinder. You do give, inflate your tire in your cycle by hand or by compressed air. If you are giving by hand, then it will be you will be using a air pump where the piston cylinder will be there. Am I right? You must be riding your bike. In bike, piston cylinder arrangement will be there or not? Yes or no? Where? In your bike. Bike means automobiles, right? Auto bike, or your car, your truck, buses, everywhere piston and cylinder arrangement will be there. Yes or no? But you people are not saying anything, right? You will be using piston cylinder arrangement where the system, we can consider this gas which is there in the piston cylinder, let us say for example, and piston will be moving, and as a result this boundary is moving, right? And there might be some heat interaction between this system and its surrounding will be nearby. So, we will be handling this kind of problems very often, and there is a we call it as a closed system where no mass transfer will be taking place. That means, if I look at this boundary, what is happening? We take a 1 kilo of mass and then we can give heat here, right? What will happen to this mass? Mass will not change, right? Okay. But however, there is a energy interaction. For example, now you are having, let us say 60-70 students are there, all of you are having, if I consider 70 students, 70 mass, like. In this system, if I look at, like you people as a system, I am interacting with you, I am basically transferring certain kind of information to you. That means there is interaction. If I take this as a system, as a student, as a all together a system, that means you are remaining here. The mass is, or the number of students are remain same. So, it is not changing, but some of you will walk down, then it is changing, right? This cannot be a closed system, and there is a interaction. For example, you imagine the student will be coming and going out, and the teacher is like, it happens in your public speech, or the wherever the politician or some other things will be coming, then people will be coming and going. That is a what you call open system. So, where you can think of a what you call fixed boundary, and there might be a closed system, right, where it is a in this case it is a fixed boundary, but in this case it is a moving boundary, is a piston cylinder, and piston will be going up and it can be come down, whereas interaction will taking place, and this is also known as a closed system because there is a energy interaction, but there is no mass change, or the mass no mass transfer is taking place, mass is remaining same. So, therefore, we call it as a closed system. Similarly, let us look at an example here, right. If you look at, this is your beautiful earth where we live. Could you see how beautiful it is? It is quite beautiful, am I right? And now the heat is coming in from the solar, we are getting lot of heat, particularly now this summer, we are getting lot of heat from the sun, and it will be absorbed by this earth surface, and so also by us, by the trees and other things, like, and lot of heat also going out. Now, I want to analyze this thing. What I will use? Can I use a control mass system or not? Yes or no? See what happened, these whites are what? This white thing, these are the atmosphere, right, around that, where if it is a sea, there will be some kind of a precipitation will be going on, vaporization of water, again condensation will be there, cloud is coming and pouring water, like rain, and there is a dust particulates, it is moving out, settling down, right. Now I want to analyze, right. Depending on what you want to analyze, we can choose the system, because choosing a system is very important. Otherwise, it will be very cumbersome, it will be very difficult to analyze the problem. How to fix the boundary, where to boundary. Suppose I want to analyze only the what? Only the energy interaction or the solar energy, whatever is coming out and in, then what I will do? I can use as a control mass system. So, where I will put my boundary? Should I put here or should I put in this place? Where should I put my what you call the system boundary such that I can use the control mass system? Where? Can anybody tell me? Is it atmosphere, right? Okay. So, if I will put it here, that means whatever changes is occurring here, right, I am not bothered, it is coming and going. So that, but if I will put it here, then it cannot be a closed system. If I put my system boundary around the earth's surface itself, I cannot consider it as a closed mass system or a closed system or a control mass system. I cannot, it will be difficult because the mass is going and out and it will be interacting. So therefore, one has to very carefully choose the system boundary, identify the system, what kind of analysis you will be doing, based on the analysis being carried out. So let us now look at the open system. Open system, both the energy and the mass will be what you call crossing the system boundary, right. Let us say you people in the winter might be using the geyser, right, for getting hot water in your hostels, am I right? So there will be heating and then water will be flowing out and in and flowing out. So then we can consider this as a flow system. As I gave an example of this room, that if the like a student will come and in going out, then it will be like kind of a open system. So if I look at that, what is happening, the solar radiation is coming and it is going out, there is a precipitation, then we will be consider this as a what you call a system, as an open system, right. For that I can take this as a system boundary, this as my system boundary. So that what will happen, like it can be basically what you call an open system, because there is a precipitation going on and it is coming going up and coming down kind of thing. I can think of a turbine, which I have done in schematically, that means some mass is entering and some mass is going out and pressure, with a certain pressure, and it is expanded and you will get the work output, and then we can consider it as a open system, and this we can take it as a system boundary, which is basically the outer casing of the turbine. So let us consider a example, because this is like if I consider this is a gas turbine engine, which is quite complex in nature, like what we use for power generation, we use for the also for like your jet engine applications kind of things, to provide the thrust to the aircraft and other vehicles. So if you look at, these are basically a compressor and there is a air intake, and then what will happening, the flow will be entering here, and when it is entering, like it will be, pressure will be increasing and you will be giving some work through the shaft. So I want to analyze this thing. What I will have to do? I will have to take a system boundary which is corresponding to this place, right. And then we will have to look at how much work is coming in and what is the change in the mass and change in the like your velocities and pressure and other things. We will have to change, look at it and then find out how it is interacting. Similarly, combustion chamber, we will have to burn some fuel and we can take this as a system boundary and look at how much change in the temperature is occurring, and you will have to look at. So, these complex systems can be looked at in a total, or you can take individual components, like in this case compressor, air intake and combustion chamber or a turbine or a nozzle, right, which is right, and each individual component you can take, analyze, or you can take the whole system and also analyze what is happening. So, depending on the things you can take, and this is an example for the open system. So, when neither the mass nor the energy are crossing the system boundary, we call it an isolated system, right. That means what will be happening in isolated system? Is it having any applications? There is no energy interaction, there is no mass also changing, or it is coming in anything. That means there is no mass interaction as such, right. Then we call it as an isolated system. We will be using it sometime, but under what condition we will use it? Any idea? Like people are isolated. How? Suppose you will do some nuisance in the society, you will be isolated, put into a jail. Am I right or wrong? So, you are being isolated. So, it is an isolated system where the interaction will be low, and you will be, and we will be using this whenever we will be talking about entropic calculation, then we will be using that. Okay? So, and as I told earlier, I am also harping it again, that particular type of system must be identified carefully for carrying out thermodynamic analysis. Otherwise, your life will be miserable for analyzing. That does not mean that I cannot use a system for to analyze. For example, if I take a problem and whether I will be taking control mass or whether I will be taking control volume, the open system is known as the control volume system also, right. Whether it is possible or not. In other words, for example, I have taken the earth and its interaction with the solar energy, right, as a system. I told that, look, you will have to take the control mass system till the atmosphere exists, earth's atmosphere exists, right, as a system boundary. But suppose I will say that I am interested to have an open system. Can I analyze it? I can analyze the same problem with an open system instead of control mass, provided I know how to do it, okay, and it may be little bit cumbersome. That means, in other words, that you can use any of them for your analysis. Sometimes it will be cumbersome to handle, but however, it is one can convert both the control mass and control volume system for the same problem. That we will be doing when we will be deriving the first law of thermodynamics for a control volume system or open system. We will be using the control mass concept and then derive that. So, we will do that later on. So, whenever a system is interacting with the surrounding, right, there will be change in the properties of the system and also the surrounding, and therefore, we need to look at properties of a system, right. And as I told earlier, a system contains certain amount of matter, and to describe a system and predict the change of state, right, we need to look at properties of the matter is to be noted down, right. For example, if I am giving some heat to a piston cylinder arrangement, the pressure will be changing, so also the temperature, and then we will be looking at those properties. So, what is the property then? Property is basically an observable characteristics of a system. That means what you can observe grossly, right? Pressure, temperature, like all those things. For example, properties of a water can be specified as what? As a colorless, odorless, tasteless, right? Am I right? Now, can these properties of water considered as thermodynamic properties? Is it possible that we can say, look at these are the thermodynamic properties? No, it is basically related to the potable condition of the water, but nowadays it is not. You see, these properties are not good enough to say whether water is potable or not. Now we are bothered about whether it is a like TDS, that is the total dissolved salt, or how much, and then what it is biological, this thing like bacteria, other things are not there. All those things we will have to consider now to make a water potable or not. But these properties are not good enough for us. For us, the thermodynamics must be associated with the energy and its transformation, or energy and its interaction with the surroundings. So, what are those properties? So, those properties are pressure, temperature, volume, mass, density, and several other things, right. So, the essential feature of properties are basically definite value at a particular state. That means you should have particular values, and also it must be a point function. That means it must be independent of the path taken by the system during its interaction with its surrounding. It should not really, right. So, therefore, one has to be consider that. So, a property at a given state is independent of a path followed by the system, right. If I consider this as a path, like for example, a system is here and it can go to another point in this, right. It can go through this path 1 to A, or it can go to A to 2, right. It can go through A to B, from 1 B 2, it can go to A to 2 3 path C. But the properties at station 1 will be not affected by the path taken. So, also the properties at the 2 it is does not depend upon what path it has taken. So, then only it will be the property of a system, right. And in order to do that, mathematically we can say properties P, I am just saying symbol using P. It can be pressure, it can be temperature, it can be anything. And let us say there is a system is interacting with surrounding, and there will be change in properties, right. Let us say the pressure is changing, right. If I take a closed chamber and then started heating the gas, then naturally pressure will increase, okay. So, if I say that the change in pressure will be P2 minus P1, and if I say the pressure is a function of x and y, I can write it down as that dP is equal to dou P by dou x when y is constant into dx, plus dou P by dou y when x is constant into dy is equal to A dx plus B dy. What is A then here? A is nothing but your dou P by dou x when y is equal to constant, right, and B is equal to dou P by dou y when x is constant, right. So, now I want to find out P as a property whether it is exact differential or not. What I will have to do? I will have to use this condition that dP is said to be exact differential only if dou A by dou y when x is constant and equal to dou B by dou x when y is constant, right. So, then property is called as a point function, and thermodynamic property is a point function, not a path function, right. It does not depend on the path. So, if you look at, we will see in the next lecture, right, how it is a mathematically we have told, physically we will look at it, and we will stop over here. Thank you.